So our first step that we need to go through in running our hypothesis test for a single proportion is to state the null and alternative hypotheses. So in that previous video, you saw some of the setup, but let's talk a little deeper about how we're going to go about this for different problems. So the null hypothesis has that notation of capital H with a subscript of 0. So we would just read that out loud as the null hypothesis. And what it represents is the current value or the accepted value, or we talked about it as the assumed value. It's our assumption about our population parameter. Or it could just be a population proportion that they've already reported. So our population parameter. But typically the structure will go, when you write this out, is we'll start by writing out null hypothesis and then colon population proportion, and then in the null hypothesis you'll always have an equal sign because the null hypothesis is assuming nothing has changed, so we assume it is a value, and then this number will come from the wording of the problem. But in terms of pieces that'll always show up is you'll always have what I'm circling right now, which is null hypothesis is p equals, and then we just need to fill in the blank for that number. Then our second piece that we need to fill in is the alternative hypothesis. So notation-wise, we write capital H with a subscript of A. You might sometimes see capital H with a subscript of 1 for the alternative hypothesis. I'm going to stick with the A version since that's most commonly used, but sometimes H1 is used for alternative hypothesis. So this is what we're trying to prove. You might see wording of what we want to find evidence for or what we want to test. And most often in the wording of a problem is the wording for the alternative hypothesis will be a little bit clearer than the null hypothesis typically. So if you look for words like evidence or test, usually nearby that is the wording for your alternative hypothesis. Now there are 3 possibilities and just depends on what we're trying to prove. So with our alternative hypothesis, so we'll always have HA and then P, and then what can change, and then the number part is going to be the same as what's in the null hypothesis. So we'll have this number that we're comparing to. So the null hypothesis will assume it is that number, and then what we're going to try to prove is either it's larger than, less than, or does not equal. And to know which form we're using, it's going to be based on the wording of the problem. So for this first case of proving that P is more than that number, some wording you can look for is if we're trying to prove that something is larger, or if something has increased, or you might just see wording of more than, something to try to prove that our value is actually bigger. And then for less than, it could be that it's smaller, or trying to prove a decrease, trying to prove that it's less than, anything that's proving that that value is smaller. And then this last one with the does not equals, we're just trying to prove that it's different. Or some wording you might see is that we're just trying to prove that there's some change. So with the alternative hypothesis, there's a little extra work to do here. But usually the wording of the question itself will tell you exactly how to fill this in, of what number you want to compare to, and then are we trying to prove that something's bigger, smaller, or just different. So what we're going to do here is go through some examples of just setting up the null and alternative hypotheses. And I am going to leave a little space to the side to the right here, because when we set up these null and alternative hypotheses, they really set up the groundwork for the rest of the test and essentially how we find p-value, which p-value is going to be the most important part of our hypothesis test because it'll tell us what conclusion to make. So for this first one, we have an old antacid provided relief for 70% of people who used it. So what they're reporting here is what happened with an old antacid. It's kind of like that's our population proportion. And then we have a pharmaceutical company has a new drug they want to test, and they want to see if it's more effective. So wording that's coming through here, that word test, like I set up above here, usually around the word test or evidence, they're giving you wording for the alternative hypothesis. So we want to test if it is more effective. So the idea is going to be, and what I could do is, even without having read that, to set up my null and alternative hypotheses, what we could do is just immediately write this down. Null hypothesis, P equals, and then I'm going to fill in the blank for a number there, alternative hypothesis P, and then for the alternative hypothesis, I have two blanks to fill here, the number as well as the symbol to use. So this population proportion, the idea is going to be with that 70% that if we make this new antacid, it should be at least as effective as that old one. So our assumption could be we made a new antacid, we're going to assume it has 70% effectiveness. 70% felt relief when they used it. So we're going to assume we get that 70% when we make this new drug. But what we want to show is that it's more effective. Now, as soon as you fill in the number there, it's always going to be the same number. So that number will always line up with the null and alternative hypothesis. So 0.7 in both, and then I just need to fill in the blank for what symbol goes in between. So 70% felt relief, and we want more people to get relief from it. So we want this percentage to increase. So we want to show that this proportion is actually larger than 0.7. So that would be our null and alternative. Null hypothesis that P is 0.7, so that those are equal. Alternative hypothesis that P is actually more than 0.7 to represent the idea of it being more effective. So the idea with this would be building evidence to see, is the proportion that felt relief from this new drug significantly larger than 0.7? What you'll notice is in the wording here, they actually left out the sample data, so we can't run the complete hypothesis test here because we don't have that sample statistic. However, what I wanted to write to the right here is how this test would end up being conducted. How would we end up finding that p-value? So what we would end up doing is we'd build this whole distribution around that null hypothesis, so around the idea that if we have this drug, we should have 70% getting relief. So in the middle here, we'd build this whole distribution around that proportion. And then if we collect this drug and collect how many people from a sample felt relief from this drug and got a sample proportion, it should land somewhere to the right here. Like we should already have something that somewhat doesn't prove, but supports what we're trying to prove. So we're trying to prove that it's more than 0.7. So when we take our sample statistic, we should have something landing to the right over here. So in terms of our p-value and how we would find it, our sample proportion would land somewhere to the right, and what our p-value would represent is if we cut there, our p-value would be the area to this right-hand side, because it's going to be that probability of seeing our sample statistic or more extreme. So what happens in these cases, without plugging any numbers in, just trying to prove that something has increased always becomes this right tail test. So this becomes a right tail test, and it's all because of that alternative hypothesis. So whenever you have an alternative hypothesis where you're trying to prove that the proportion is larger than some number, when we go to find p-value, it's going to come from a right tail when we do our calculation. So that's just to show that in general, how a right tail test comes through. It's all because of that symbol in the alternative hypothesis. All right, in part B here, a company is concerned that too few of its cars meet pollution emission standards. They have 1,500 cars and they sample 56 cars and find that 43 meet emission standards. Now they're giving sample data here, and if I'm in the stage of setting up null and alternative hypotheses, we want to completely ignore that. It's important later on. In fact, when it becomes important is right here in calculating p-value, and that's the only point in our test where we use our sample statistic. But setting up null and alternative, ignore any sample data. That's not going to be part of it. So they want to test. So there's our keyword that gets us at our alternative hypothesis. They want to test if less than 80% of their fleet meets emission standards. So setting up our null and alternative hypotheses here, and we'll have P equals in the null hypothesis and P in the alternative hypothesis. And this wording right here sets up our alternative exactly, less than 80%. So we want to prove that this is significantly less than 0.8, which means our null hypothesis is that we're going to assume it is 0.8. So even though they don't say anything about the population parameter being exactly equal to 80%, that's okay. It really comes from the alternative and setting up there, and then those numbers have to always be the same. Now with this scenario and running a test and finding p-value, we would set up our sampling distribution around that 0.8 or whatever our population proportion is. And then if we're trying to prove that our proportion is significantly less than, when we take a sample, we should be landing somewhere on this left-hand side. We should be getting a sample statistic that's smaller than our population parameter, or what we assume is our population parameter. And then our proof, our p-value, is going to come from, well, what's the probability of seeing that value or more extreme? Then when we go to find p-value in this case, we're going to go to the left-hand side. It'll be the probability of seeing a sample statistic that small or even smaller. So this, when we use the less than symbol in the alternative hypothesis, that's going to make a left tail test. So whenever you see the less than symbol in the alternative hypothesis, your p-value is going to come from the left tail. All right, and then our last one here is the official poverty rate was 14.8% in the US in 2014. A city official wants to test, so there's our keyword, if their county has a different poverty rate. So, null and alternative hypotheses. Null hypothesis, we would assume the county has the same poverty rate as the rest of the United States, and we're trying to prove that it's different. So notice they're not trying to prove that it's larger than or smaller than. With this, we'll have that does not equal symbol because we just want to show that it is not 0.148. So we just want to show that it's significantly different. Now, this test is a little special, and we'll talk about kind of the two ways it can show up. This is called a two-tail test. So this will occur whenever you have the does not equal symbol, when we're trying to prove that p is not equal to some number. So there's two ways this can occur. One way that this can occur is setting up our sampling distribution all around that population parameter. So in this case, it would be set up around that 0.148. If we take a sample, this is where it's kind of splits into two possibilities. It's because that sample could either land above or below. Because we're just trying to prove it's different doesn't suggest a specific direction. So let's say we land on this right-hand side. We take a sample and we see something larger. So the probability of getting our p-value is going to come from the probability of that test statistic or more extreme. But this is a little incomplete because what we have here is just a right tail test, only proving that it's larger than, and we just want to show it's different. So what ends up happening here is with this value here, there is this probability of it being that different or even more different. But in terms of difference, that happens in a positive direction and negative direction, meaning there's this equivalent point on this left-hand side here that is equally different from that population parameter as our sample statistic was. So what we have is this symmetric point, which is about here, that would also be just as different. And so in terms of p-value, we want to see the probability of being this different or more different. So what ends up happening, even though our sample statistic's just making this right tail, there's this symmetric equivalent tail on the left-hand side that's adding to this probability of just being different. So what we would do here in terms of calculation for p-value, because our p-value is going to be the combination of those two tails together, so we'd add those probabilities. So with our p-value, what we would do in this case is in GeoGebra, what will occur is you'll find this area for right tail, so you'd basically run it like a right tail test, but then whatever area you get out there, you'd multiply it by 2. So you just double it because we have the symmetry, so you don't have to go and find that cutoff point and then find the area. It's just whatever area comes from that single tail, you have to double it because we're just looking at difference. So what you do is take 2 times and then whatever that tail area is. Now, the second case that I mentioned before is very similar. It's just what if our sample statistic landed on the left-hand side? And we basically do the same thing. The idea being if we took our sample statistic and we landed on this left-hand side, so you take the probability of that value or more extreme, but that's just our left-tailed test trying to prove that it's smaller. So we need to bring through that idea again that there's this equivalent piece on the right-hand side this time that's equally different. And so we need to add on the probability of seeing that value or more extreme as well. So this case, what you'd end up doing is you treat it like a left tail test. So you'd find the area of this left tail, and then whatever that area is, multiply it by 2. So basically, whenever we have these two-tailed tests, if you're trying to prove change or difference, you're going to have this little extra step of needing to multiply by 2 once you find that tail area. But when we have left tail or right tail, you just need that tail area, and that will be your p-value. So this is how we'll set up null and alternative hypotheses, and then relating that also to how that will set us up to how we calculate our p-value when we get to that step. So this is our first step of our hypothesis test.